Hello. In a previous video we saw some mathematical properties of spin-half systems. So we were thinking about electrons with their spins. We were passing them through Stern-Gerlach apparatuses, which separate them according to whether they have spin up or spin down in a given direction. And we saw various interesting properties that you can find. So I don't have a Stern-Gerlach apparatus to show you in my bedroom, unfortunately, but I do have an equivalent experiment we can do involving the polarization of light. So in a Stern-Gerlach case with the spin of the electron, the orthogonal states in the quantum mechanical sense are spin up and spin down. In polarization, it's vertical polarization and horizontal polarization. So remember, the polarization of light you can think of as the direction in which the electric field is oscillating. If we take a polarization filter like this, you can see that it's blocking some of the light, so it should be blocking about half the light. And what it's doing is letting in the light that has linear polarization, so an electric field oscillating in one direction, and let's say it's up in this case. So one of the things we saw in the Stern-Gerlach case was that if you can prepare an electron which certainly has a spin up in a given direction, say Z, and then you perform another measurement on spin up in the Z direction, another measurement in the Z direction, it's guaranteed to give the answer spin up again. Okay. So in the Stern-Gerlach case, we split a beam of electrons into spin up and spin down. Then we block the down beam, and now this remaining beam is all spin up. We pass it through a second Stern-Gerlach apparatus in the same direction, and we again block the down beam, and we find that everything that got through the first one got through the second one. And similarly, if we measure in the same direction the second time, but we try to let only down through on the second one and up through on the first one, then 0% of them will get through. So we can see all of that with polarization filters. So here's a polarization filter. I'll bring it quite close so you can see it. Okay, so you're looking at polarized light through there. Now I'll bring a second one in, and you see there should be basically no change, because all the light that gets through one gets through the other. Okay, so now I'm going to take the second one, I'm going to rotate it 90 degrees, which is the equivalent of spin up to spin down. And you see that now no light gets through. Okay, because if it's getting through the first one, it must be vertically polarized. If it's getting through the second one, it must be horizontally polarized, and nothing can have both of those. It's effectively making a spin half measurement in the same direction twice and asking it to do opposite things. But the really weird thing we saw with spin was that if we measure in Z, say, and we find it to be spin up, if we perform another measurement in Z, we'll find it to be spin up again, and we can measure it as many times as we like. But if we perform an intermediate measurement in a different direction, 90 degrees, say spin in the X direction, it'll have a 50% chance of being either up or down in the X direction. But then it's well defined in the X direction. We select out, say, all the ups in the X direction, and now we pass it to a second Z filter, and now it has a 50% chance. Anything that gets through that X filter has a 50% chance of being either up or down in Z. So whereas if we keep measuring in Z, we'll keep finding the same answer, if we make an intermediate measurement in a 90-degree rotated direction, we will randomize the result. So we can do that with polarization filters. So again, here's one filter. Here's a second filter that's at 90 degrees. Let's just check. Here's everything getting through. Here's nothing getting through. And now if I bring a third filter, if I put it in front of the first two, nothing will happen. If I put it behind the first two, nothing will happen. And if I put it between the two, something will happen. There you go, you can see me. Let's try that at that angle. There we go. So you can see me through that, right? So here, nothing getting through. I put an additional filter in, and something gets through. So what we're doing is we're measuring, we were only letting vertically polarized things through this one. If we let only horizontally polarized through this one, nothing gets through. But if in the meantime we make an intermediate measurement at 45 degrees, like this, which is the equivalent of a spin X measurement on something that was spin Z before, and then we pass a second filter, now something gets through. Okay, so it's a little demonstration you can do at home, which demonstrates these mathematical properties of spin a half. In general, it's a two-dimensional Hilbert space of quantum mechanical particles. All right, thank you for your time.